All right, today we are going to talk about a new kind of ion. This ion is called complex ion. This complex ion comes from something that's already formed an ion. So there has to be one ion already for the complex to be made. And the reason it is possible to use that ion to make bigger ions is because the 3D metal ions that you have, एक तो बहुत छोटे होते, they have a really small radius, and at the same time they have a high charge density. They have a very strong effective nuclear charge. So they are able to pull on things that aren't even charged, like things that don't have a negative charge on them. Sure, positive ions attract negative ions. That's pretty common. These things, they're able to pull on individual electrons within other molecules. They're that strongly positively charged. So, for example, if there's a lone pair, these will pull on those lone pairs. And then they will make dative bonds with them. So the thing that brings in a lone pair, it's a base and we call it a ligand. So ligand is a base with obviously lone pair that shares it or makes a bonds with metal ion. Now, of course, lone pairs are present in neutral atoms as well as they are present in anions. Similarly, how strongly these lone pairs are pulled depends a lot on what thing has those lone pairs. If a ligand is very strongly electronegative compared to the metal, and you know that metals have pretty low electronegativity. So if the ligand has fluoride, for example, then even though it makes a bond with the metal ion, it's still not going to share it very graciously, very generously. It's going to keep the lone pair to itself because of its high electronegativity. So even though a dative bond is formed, that bond is not that strong because it's not really doing justice to the idea of sharing here. But if it is something like carbon and that has a lone pair, then when it shares that, it shares it with a more open heart, wholeheartedly. And because of its low electronegativity, carbon is able to make a much stronger dative bond than nitrogen, for example, or oxygen, for example. So these ligands, they make dative bond with the metal ion, and we show it as an arrow, of course, just like we show others. And more electronegative ligands make weaker bond, which means that a more stable complex ion can be made from a less stable complex ion. You can have a ligand which has a lower electronegativity come in and replace a ligand that has a higher electronegativity. Why? Because the one with higher electronegativity has a weaker bond. To figure out the stability of any such ligand exchange, ligands can be exchanged. We use K stability, the K stab value, to compare them, used to compare this strength or stability of these bonds, the dative bonds that they make. Now, what did I say? The one with lower electronegativity makes a better ligand, a stronger ligand. So cyanide ion is a much stronger ligand than ammonia. Even though they both have nitrogen in them, in the case of cyanide, the lone pair is coming from carbon. In the case of ammonia, the lone pair is coming from nitrogen. Then you have halides. And for a number of reasons, these halides, even though a bigger halide should be less stable, which it is, yet they usually are better or stronger dative bond than water in the case of central ions. There are some reasons for that. Now, you can have 2, 4, even 6 ligands attach to one metal ion. And based on that, the geometry of the complex ion that you get is going to change. Is this an acid-base reaction? Any reaction in which data bond is made is an acid-base reaction. So it is an acid-base reaction. Will there be an equilibrium? Of course, there'll be an equilibrium, just like other acid-base reactions have equilibrium. Can a positive ion make a ligand? Positive ions usually have empty orbitals. They don't have lone pairs to spare. Secondly, they will push the central metal ion away. So positive ions cannot make or act like a ligand. But neutral atoms, neutral molecules, neutral or negative ions, they do this all the time. You just need lone pairs. So how do we show ligand? So let's take the example of iron, for example. Iron with a positive 2 charge. Let's say I reacted with oxygen. Water. Now I can have 6 waters, maximum 6 water molecules to bond with this. And they can have dative bonds like this. So there'll be H2O like this, H2O like this, H2O like this. So 6 water molecules can bond with 1 iron 2. But together, they are all neutral and iron is still positive 2. So the overall charge is going to be there. We show this as iron with 6 water in the brackets and a square bracket to show that this is a complex ion. The ligand is water, and this whole thing is the complex ion that we have. Okay? How do we name it? We say this is hexa aqua iron 2 complex. That's what this is. So there's 6 water molecules bonded with this. Now, many times it's easy to identify what the ligand is. For example, if I said nickel with 4 cyanides, and let's say this is nickel positive 2. Every cyanide is negative 1. So that's -4 + 2 and overall -2 charge. And this one, we can easily see that cyanide is a ligand here. So we can say it's tetracyano nickel 2 complex. And we can easily identify that which one is the ligand, which one is not. But sometimes it's not as straightforward. What if I have like chromium 3+ and I write it like this? Now I don't know which one's the ligand and which one's not. Why? Because it is possible that I might have Cr with 6 ligands and positive 3 charge bonded to 3 chlorides. So there's no chlorine ligand or chloride ligand, but there are 3 chloride ions that have bonded to this complex, and that's fine. Or I could have a combination of that. I could have 5 water molecules as ligands, 1 chloride as ligand, making an overall positive 2 charge. And I could have 2 chlorine chlorides and 1 water, and I'll show that as a dot. And that is also a possibility. So it is important that we specify which ligand it has. And the only way to do that is through the shape, the diagram. And VSEPR doesn't always work here. That's a problem. VSEPR has its fair share of where it works, but in some cases it won't work here. And that is when you have 4. So let's look at what different shapes we are going to get. So there are 4 different shapes that we can get. First one is if you have 2 ligands. So with 2 ligands, The metal ion is in the center. Let's take the example of silver, for example, silver ion. And let's say it is the ligands are ammonia. So ammonia has a dative bond here. Another ammonia has a dative bond here. It's a pretty linear structure. And this is a positive one. So we say this is diamino silver or diammonium silver complex. Okay. We should say diammonium though. Diamino can be misinterpreted. What if I have 4 ligands? In the case of 4 ligands, I will get, let's say, platinum. So platinum can have 4 ligands, but then how are those 4 ligands going to arrange themselves? Are they all going to be in the same plane, or are they all going to be in different planes? So it varies, and it depends on a number of different things. So in a molecule like this, in a complex like this, these are all in one plane. So 2 of them are behind and 2 of them are in the front. Or you can also draw it like this, because they're all in the same plane. And this one has a positive 2 charge. This one we'll call a square planar shape. This one we'll call a linear shape, linear geometry. Well, it is possible, and especially in the case of smaller ions or that are well, there are different reasons why that will be the case. So for example, in the case of copper, for example, then it is possible that copper will be attached to 4 ligands in a tetrahedral shape. Or cobalt even. Cobalt does the same thing. I will show the positive 2 on this side. Now this is a tetrahedral shape. So even though both of them have like 4 ligands, tetrahedral shape bhi ho sakti hai, square planar bhi ho sakti hai. They can be in the plane and have a 90-degree angle, or they can be tetrahedral and have 109.5-degree angle. The overall charge is going to be 4Cl, so that is -4, 2 copper, so -2 overall. And then we have 6 ligands. In the case of 6 ligands, it is always going to be octahedral. So let's say I have a metal in the middle, iron, for example. So iron can have 6 ligands. So water. In fact, let me just draw the tetrahedral structure for this. Oh, sorry, the 3-dimensional structure for this. So H2O, wedge to show H2O. This is at the bottom. And this is at the front. So this is a positive 2 charge. Yeah. So this is an octahedral shape. Why octahedral? Because if I were to join these 4 will make the base. And I could make a pyramid at the top and another pyramid at the bottom. And this is a tetrahedral shape. Oh, sorry, octahedral shape. Yeah, just to make things more clear. I don't know if that worked or not. But yeah, this is a octahedral shape. And this octahedral shape is telling me that Vesper is still somewhat there. This is the only case where Vesper doesn't entirely work for us. And that's fine. So there are 6 ligands making octahedral, 2 ligands making linear, and 4 ligands make it either square planar or tetrahedral, one of the 2. Exact reason for why that works, we don't have to go into that. Okay, so those are the ways we can see different ligands coming in, and we can figure out, okay, which one is going to be there. Now, the central atom, depending on how many dative bonds it has made, we call that a coordination number. So in this case, the coordination number is 6. In this case, the coordinate number is 4. And in this case, it is 2. So these numbers that I was writing, they were actually the coordination number of the central metal ion. And it does not matter whether one ligand makes one bond or two bonds or three bonds or even six bonds. The central metal atom is what we're going to look at to figure out कि अच्छा उसका coordination number क्या है. Now ligands, as I said, they can make multiple bonds. They can have, like we can have very large ligands, and those large ligands can join with the central metal atom like a claw or from multiple sides. And that is what we call these things actually. The word for when you have central metal atom joined by one ligand, which is so big that it has surrounded it, the word is chelate. Chelate is usually the term that we use to describe that it's a complex in which the central metal atom is joined to a ligand through multiple dative bonds, because it's kind of like claws onto this thing. The chelate is actually coming from the word for claw. Okay. So what's a chelate? Let's take an example. Let's say I have iron and I have a ligand that makes two bonds. So one ligand that does that is ethane diOate. So we usually write it as OX. Okay. So we will say Fe with OX3 because every OX can have two bonds. So OX3 because the total 6 bonds can be there. And of course, the overall bond is going to be like this. So what is OX? OX is OOC bonded to COO with a negative charge at lone pair at the end of it. So here's what it does. The O part makes a dative bond with iron. Of course, it is there like that. And then makes a dative bond with what? Iron again. Just look at this thing. Doesn't it look like something is holding on to iron? It's kind of like pinching iron. It is a claw that's holding on to iron. So that's what we call a chelate. This whole thing is a chelate. And the OX here, which is this whole thing, ethane diOate, is the ligand that has made two bonds. And that is why we call it bidentate ligand. Okay, so bidentate ligand. So this ligand has made two bonds. Water was a ligand that was making just one bond. So water was the monodentate ligand. It had just one lone pair that was able to use to figure out or to make the dative bond. But this is a bidentate one. It is able to form a ring around water like around the iron like this because of two lone pairs. You can also have another one which is called En in our syllabus. Okay, En is similar to COO, sorry, COO twice, the ethane diOate. The exact name of this thing is 1,2-diamino ethane, but we don't have to get into the details of that. What exactly is it? It is diaminoethane. So there's the ethane part, there's two aminos, one on each side. Okay, that's what this is. Now, the nitrogen over here has lone pairs. And those lone pairs can make bonds with the iron in there. So just like ethane diOate was able to do it, the OX thing, En thing is also able to do this. So the nitrogen in here is going to make dative bond, and then the carbon is there to make sure that the claw thing is made. And there you go. So again, this is also a chelate made by a bidentate ligand. It's as if I'm speaking French. There's so many weird words. But just remember, bidentate means ligand with two lone pairs to donate. Chelate, not that much of an important term for exam. The coordination number is a more important term for the exam. So coordinate number for this particular ion in this case is 2, but I'm not done with it yet. This ion can be joined with multiple of these. So I can have 3 En in total. Why? Because up to 6 bonds can be made. And in this case, I will obviously have one from the top, from the left, from the right, from the bottom. And that way we are able to get the 3 ENs there. Okay. So EN and OX. These are two bidentate ligands in our syllabus. There's one more case, which we call a polydentate ligand. A polydentate ligand would be one which makes many different dative bonds. One of those is ETA, EDTA. ETA is a huge molecule. It is able to bond with the central metal line in a way that it makes 6 bonds. 6 bonds. One molecule. So it's able to surround the metal line har taraf se. When I imagine ETA, I kind of like think of Spider-Man, the first movie of Spider-Man, the early 2000s one, in which there was this guy which had so many arms. I don't remember exactly who it was. It was some doctor. And he's able to hold on to Spider-Man right in the middle. So this metal line in there, that's the Spider-Man being surrounded by so many arms coming from ETA. So it's kind of like this. The metal line is in the center. And it can make 6 bonds, obviously. And ETA is going to do that. ETA is going to bond with one with oxygen, another with oxygen, one with nitrogen, another with nitrogen, another with oxygen, and another with oxygen. So what it does is that this one, I think it is like this. And there's another one like this. And then these are joined together. And this is joined to, sorry. This is joined like this. And then it is joined like this. So kind of like this. So it's a huge molecule that is able to bond with this. Of course, there's lone pair here, but still there's a negative charge on each of these oxygen. And each of these nitrogens just has a lone pair to donate. So it is able to make these dative bonds. In fact, let me show you through a 3-dimensional shape to show that this is in the front. This is in the front. That one is in the back. And that's how they kind of like surround the central metal line. ETA has a -4 charge. Okay. So it has a -4 charge. So when you bind it with, let's say, M with a +3, you're going to get M with ETA with the overall -1 complex. Okay. The actual name of this thing is ethylene diamine tetraacetic acid. Why? Because ethylene, 2 carbons in the middle, these ones. Diamine, these 2 nitrogens. Tetraacetic. Each of these arms is an acetic acid, the carboxylic acid part that comes in here to make this. But of course, we'll just call it ETA. Okay. So we have so many ligands there that are able to do this. So let's see if you actually understand what I'm saying. Can you tell me that if I had cobalt with 6 ammonia, number one, what will be the shape of this complex? Because I have 6 ligands, the shape is going to be octahedral. That's one. Okay, what is the charge on cobalt here? +3, because ammonia is neutral. Now let me change that a little bit. Let's say I have chromium with 6 hydroxide ions. Now this is chromium 3+. What is the overall charge? So OH is -1. The overall charge is going to be -3 because 6 times -1 is -3, and then I have +3 from chromium. So overall -3 charge. Okay. This one is going to be called hexahydroxy chromium 3 complex. That one is called hexaamino hexammonium or hexamino, cobalt, cobalt 3 ion or cobalt 3 complex. Okay. So does everybody understand that how these are going to make different shapes? What is their names? And how we can have monodentate, bidentate, and polydentate ligand. Just like in the case of other tetrahedral things that we saw in organic last year, these ones are also going to show isomerism. And remember, we had tetrahedral structures that were showing uh, what was that? Optical isomerism. So just like that, over here, we're also going to see that for tetrahedral shapes. But more than that, we're also going to probably see that for the octahedral shape as well. So here's an example of how an octahedral shape can show us uh, cis trans isomerism or stereoisomerism. So let's start with stereoisomerism. Let's say I have this complex cobalt with 2 En and 2 bromides. Okay, so that's what I have. Now bromide is -1 and En is neutral, so overall the charge is going to be 0 because cobalt is also +2 in this case, let's say. So what will the octahedral shape look like? Even though I have 4 ligands, the coordination number is still 6 because it's still going to make 6 bonds. So I'll put the cobalt in the center. I will draw the 2 bonds behind, 2 bonds in the front, 1 at the bottom, 1 at the top. Okay, now let's try to put this. One possibility is that I join 1 bromine here, 1 bromine here. If I do that, if I put 1 bromine here and 1 bromine here, that leaves me these 2 for En. So this one with En and this one with En. And that's pretty straightforward. I can do that. This thing, if I reflect it, let's say I reflect it, I will get the same thing back. Bromine at the top, bromine at the bottom, this En, this one reflected here, and this En reflected here. No optical isomerism, no stereoisomerism. So this is not isomer. So this is only one isomer so far. But what if I had the same thing, but this time I put bromine on sides, not at top and bottom. Let's say I put them here. Now I've left these 2 for En or these 2 for En, right? So let's see. If I put this for En and this for En, I have this shape. So it's important that you're able to imagine that En is basically coming at it. This one is bonded to it behind the screen, and this one is bonded to it in front of the screen. Now, if I reflect this one here, in this case, I will get bromine here, the bromide here, sure. But more than that, this one is going to show stereoisomerism. Because no matter how much I rotate this thing, it is never going to show me this way. And that is a very important thing to remember. I may never get this one and this one to be the same. These are isomers. Okay. This one, if you look at bromine, then they are being separated by this plane of En. This one is called the trans isomer, and this one is called the cis isomer. The cis isomer has 2 optical isomers. So there's the second one and there's the third one. They're both cis. Why? Because the bromine are both on the same side. And this one is trans, it has just 1 isomer. So overall, we have 3 isomers from this one complex. How does complex show up in Uh, Square planar. Let's see. Cisplatin is a very useful uh, molecule or complex that we use. Okay. Here's how it goes. So we have platinum with two chlorine and two ammonia. Let me draw the platinum in the center. And this one is square planar. So I have two options. Either I can put both the chlorines with next to each other, or I can put them opposite to each other. Let's say I put them next to each other. And so ammonia goes at the back. Or I can put them opposite to each other, in which case the ammonia goes one in the front, one in the back. This is cis trans isomerism right there. This one is trans and this one is cis. This thing is called cisplatin and that one is called transplatin. Cisplatin has the usage in cancer treatment. Not all cancers, but some cancers. What happens is that DNA, whenever cancer is basically uh, a rapid growth of cells, right? So what happens is that one of these chlorides is displaced by water. What happens is that when I add water to this, ligand exchange happens. And one chloride is displaced by water. And that forms a complex. That complex can bind to guanine, the one of the four bases in DNA. Now, when that happens, the rapid copying or replication of the DNA that was happening is stopped. And so when the DNA cannot be copied, you guys study bio, you know bio more than me, the cancer cannot grow. And so it dies. So just because this inhibits DNA replication through ligand exchange, not as it is. So cisplatin undergoes ligand exchange when hydrolyzed. And that hydrolyzed one binds to guanine and inhibits DNA replication. And so it is useful in treating cancer. So we have seen that you can get optical isomers in the octahedral shape, in the tetrahedral shape, we already know that, in the square planar shape, and in all of these geometries, these show up in different ways for us to like analyze them. In the next class, we will talk about how color comes out to be. But before that, I need you to memorize 6 different complexes and their colors. I will send you the table for that. Okay. Thank you so much. Take care. Allah Hafiz.